Today we're moving on from theoretical things, from the mean value theorem, to the introduction to what's going to occupy us for the whole rest of the course, which is integration. So in order to introduce that subject, I need to introduce for you a new notation, which is called differentials. I'm going to tell you what a differential is, and we'll get used to using it over time. If you have a function which is y equals f of x, then the differential of y so is going to be denoted dy, and it's by definition f prime of x dx. So here's the notation. And because y is really equal to f, sometimes we also call it the differential of f. So it's also called the differential of f. Now that's the notation, and it's the same thing as what happens if you formally just take this dx, act like it's a number, and divide it into dy. So it means the same thing as this statement here. And this is more or less the Leibniz interpretation of derivatives. Of a derivative as a ratio of these so-called differentials. It's a ratio of what are known as infinitesimals. Now this is a kind of a vague notion, this little bit here being an infinitesimal. It's sort of like an infinitely small quantity. And Leibniz perfected the idea of dealing with these intuitively, and subsequently mathematicians use them all the time. They're way more effective than the notation that Newton used. You might think that notations are a small matter, but they allow you to think much faster sometimes when you have the right names and the right symbols for everything. And in this case, it made a very big difference. Leibniz's notation was adopted on the continent, and Newton dominated in Britain, and as a result, the British fell behind by 100 or 200 years in the development of calculus. It was really a serious matter, so it's really well worth your while to get used to this idea of ratios, and it comes up all over the place, both in this class and also in multivariable calculus. It's used in many contexts.